And I promise you CV will pop up in spots where it's not just constant volume. We'll see some cool stuff. Okay, we're gonna follow a very similar procedure for constant pressure heat capacity. We're gonna name or give this guy the symbol C sub what? Yep, we're really creative. So we're gonna go with. Okay, we already came up with an expression for dH. What did we say H was gonna be a function of?
Pressure temperature.
Yep. And then we came up with this differential. We said it earlier, right? What order did we do it in, just so I keep the same order? dH. We did P. We did T constant. P. Partial of H. Partial of T. Okay. Here we want to take a bit different of an approach. Last time we did some derivation. We got to a point where we hit our heads against the wall and we couldn't move any further, and we had to assume our constant volume conditions. Here, let's just get to the point. Under what conditions are we considering? Yeah. How's that going to make our equation easier? Yeah. So, what we're left over with, I'm going to leave off some of this stuff. pH is equal to H, partial temperature, pressure constant, T. Okay, but how did we define heat capacity again? It was something over something. What was it? dQ
over dt.
Okay. I see a dt. I don't see a dq. Is there any relationships we know that could help us get to a dq somewhere in here? What is H again? Okay. What is that thing? All right, let's be simpler. What's that thing?
Enthalpy of the reaction.
Yep, enthalpy of a reaction. Have you ever heard it said any other way besides enthalpy of a reaction? Yep. When is the heat and enthalpy equivalent to one another? Yeah, constant pressure. We proved that a while ago, right? So delta H is equal to Q sub what?
Eight.
Yep. Now let's say we have dH. What's that going to be equal to then, under our conditions? Yep, PQ sub P. So what can we do here to find a Q? Yeah. Those two are equivalent to one another, right? Okay, what do you suggest to do to get to a heat capacity then? Yep. And what we end up with is Q sub P T what is this thing?
CP.
Yep. That's pretty nice. Let's just take it from this step back though. Let's say I want delta H, which is also equal to what in this case, given we're at constant pressure? Yeah. How am I gonna go from here to here? Yep, we need an integral. Okay, how can we simplify this? Oh, we also have some temperature bounds, Ti, Tf. How can we, what are we gonna do here? Yeah. We got Cp, Et. Now, technically, this is a function of temperature. If you look in your book, there's a bunch of different formulas for determining what Cp is over a wide range of temperatures. What can we do most of the time? Okay, so Cp is meant to be a function of temperature, but what can we approximate it to be? Yeah, just a constant. If that's the case, delta H is equal to, what can we do with that Cp?
Take it out.
Yeah, pull it out, and look at that. Gotta love easy integrals, what's that one?
CP delta T.
Yeah. Awesome, now we have enthalpy in an easy way to get it. All we have to do is look up that constant pressure, heat capacity, and we have an enthalpy now. So we can just look up values and get those, which is great. Okay, when is this true though? What approximations do we have to make?
Constant pressure.
Constant pressure, and what else?
Like CP is constant.
Yep, Cp is constant over whatever range we're considering. Okay. Does that make sense?